Mhm. All right, today we have Karapet Mkrtchyan tell us about democratic nonlinear p-form electrodynamics. Take it away.
Thanks a lot, Julius, and thanks for the invitation to speak in the Quiver meeting with not so Quiver talk. But I think the subject I will discuss today is generically familiar and interesting to the people of this audience. And most of it may be too elementary, but still, I think it's worth to revisit this story. So I will talk about mostly about electrodynamics in 4 dimensions, and then I will mention generalizations, but it's all about the simplest and the oldest field theory we know, and it's all classical. So let me start by some motivation. Well, about the references, I will not give much references, just to mention in the beginning what is it based on. It's a program I started in 2019 with the work that was very much inspired by some discussions with Arkady Tsvetlin. And the original aim was to study potential formulations of Lagrangian for non-abelian two-form systems, which is, as we know, very complicated, but still expected that it should exist in 6 dimensions. So this problem has somehow led me to try some things, and I came up with some interesting news about general problem of formulations for chiral fields, and not only chiral but also democratic formulations for p-forms. And then this program has been continued in collaboration with Oleg Evnin and one of his postdocs, Sukruti Pansal, in 2021. And then we took it away from there with Quiver Meeting and Oleg Evnin last year. And most of the discussion of this talk will be based on these 2 papers with Quiver Meeting and Oleg Evnin, which is so the first one is mainly about electrodynamics in 4 dimensions, but nonlinear one. And the second one is generalizations to p-forms and some theorems proving the consistency of the construction. But in the meantime, this approach of chiral field theories, we have somehow applied it with Friedrich Wallach on the formulation of supergravities in 10 dimensions successfully. And also we have a review with Oleg Evnin, where we actually explain relations with other formulations and try to argue that our formulation has advantage compared to others. And I will mention this in the end. So the motivation that I started with was related to the 6-dimensional two forms. Although this problem of electric-magnetic duality, it appears in many different contexts and has been always subject of amusing thoughts for me. But when actually starting to try to construct interactions for two forms, this is how I came to this program. But also generically, of course, the original problem is not yet solved, and I still hope that eventually this program may lead to a solution of it, but that's an ambitious task. So generically, there are several ambitious problems in field theory where I believe this knowledge gathered in this program may be applied. So one is the construction of trying to understand the non-abelian p-forms. As we know, there are many indications from string theory that this should exist, but there's no field theoretical description so far in terms of Lagrangian. There are several proposals, but each of them have some flow that does not allow to either unitarity issue or locality or other things that does not allow to settle on that. On the other hand, there are other problems in standard gauge theory, like Monton and Olive duality, its various reincarnations, extensions that appear, and probably people in this audience are more familiar to those than I am. But the question is whether the S-duality that appears in gauge theory, non-abelian gauge theory, can be manifest. And this again would require a new approach to gauge theory with a different setup. And I hope that the setup that we start here may be applied to this problem also. There is another issue of magnetic charges. We know the Dirac monopole. We know that there is a problem of classical description of theories where there are also magnetic charges. And again, this story somehow has issues with locality or Lorentz covariance, so on. And I hope that we may have some progress also in these directions eventually. And generalizations of manifest electric magnetic duality to gravity and higher spins are also studied in literature, mainly by Brussels group, Marc Henault and collaborators. And I believe that also our approach might be generalized in these directions, might have some applications. So I start with the simplest field theory example of duality-symmetry, which is the electric magnetic duality of four-dimensional electromagnetism without charges, without sources. So we have just Maxwell equations for free electromagnetic field. And here we know that there's a duality rotation symmetry that rotates electric and magnetic fields. And as a particular part of this symmetry is the discrete electric magnetic duality, which interchanges electric and magnetic field vectors. So this symmetry is a symmetry of equations of motion, but not of the Lagrangian in Maxwell theory, when we describe the Lagrangian in the standard Larmor form. When we when we add the sources, usually in standard QED, we have only electric sources, we don't have magnetic sources, and that breaks this symmetry of the free theory. While if one wants to restore this symmetry, one has to introduce magnetic charges and correspondingly magnetic currents. And here we would have this equation would have a symmetry with rotating also electric and magnetic charges, while Lagrangian that would give this equations is not known. Furthermore, so we would like to define eventually a Lagrangian also for the free electromagnetic theory, for which the electric magnetic duality is manifest. And this has been a problem since 50 years, and there are several solutions proposed. We propose yet another solution, as I will show later. So the standard Lagrangian, where we have a single gauge potential, is given in a standard Larmor form. And here we know that even the discrete electric magnetic duality is not the symmetry of this Lagrangian. It changes the sign of the Lagrangian. On the other hand, one can write equations of motion in the form of so-called twisted self-duality relation, where we employ two potentials, electric and magnetic, quote unquote, which the Hodge duality relation between the two curvatures of these potentials is equivalent to Maxwell equations. So these equations, although naively they are not Lagrangian, they would describe correctly what we want. We want to have Maxwell equations, but with the electric magnetic duality symmetry manifest coming from the Lagrangian. And now we would like to write a Lagrangian that would give us this equation. So generalization of this problem is related to p-forms. So we start from any p-form given by potential A. Then we have the curvature, which is a p+1 form, and then we can write an analog of the Maxwell-Lagrangian, which is f(h star f), and this would describe a theory of a p-form. On the other hand, there's a dual theory, which is described by t minus 2 minus p form, and the particle content of these two theories is the same, while it is hard to say whether these two would have the same interacting deformations. In general, it's not true, and that means that the choice of the variables in the free theory already determines what kind of interactions one can have. And of course, we need to also impose locality, unitarity, and so on. So this is very important to have a generality in our description for the free Lagrangian, and also given that in a certain formulation we are not able to find certain interacting theory, which is the case for this mysterious theories like 2,0, does not yet mean that this is not possible to describe with the Lagrangian. It just means that the starting point of our free theory might not be the right one for the description. And here one can understand this duality is, I think most of the people here know about it, but just a simple way of understanding this duality is that the p-forms in the standard Lagrangian form, they describe a particle representation, which is the p-form representation of massless little group. And then in the same way, the same is true for t minus 2 minus p form. And then since the little group is ISO t minus 2, and the representation that we are discussing here are massless representations with trivial action of the non-compact part, then these two are dual each other also in the sense of Hodge duality of the little group. While of course we know that the standard duality is that we relate the curvatures of the two forms in the Lorentz covariant manner. So, so the equations of motion for such a system where we have p-form particles, in a sense, described in a democratic manner, where we have both p-form and the t minus 2 minus p form entering the description. This problem is very analogous to the electromagnetic twisted self-duality equation in 4D that I described. And this equation would require introducing two potentials, one p form, one t minus 2 minus p form, and writing equations of motion, which are twisted self-duality equations, saying that one of them is the Hodge dual of the other. And this writing a Lagrangian for such, so that we would get such formulation or such equations as Euler-Lagrange equations from the Lagrangian is not a tricky question. The problem of duality-symmetric formulations have been raised and studied by many people. I mentioned here some of them throughout many years. So at least 52, if we start from Zwanzinger's work. But writing a Lagrangian has been always a tricky problem, and the main progress is so the Zwanzinger formulation is losing the manifest Lorentz covariance, while the first example where people managed to construct such a system with the right equations and the manifest Lorentz covariance in the Lagrangian is the Pasti-Sarokin formulation, also known as PST formulation. This formulation is somewhat related to what we are doing. I will mention some relation between them and also the differences. So the the strange thing about the p-forms is that, okay, so these are very dimension dependent, the possibility of writing self-duality equations. As we know, in 4 dimensions, we cannot write self-duality equation for Maxwell field in Lorentzian signature, but we can write in Euclidean signature, and this is the instanton equations well studied. While in the Lorentzian signature, one can write the twisted self-duality equation, where you have 2 different potentials and their curvatures are Hodge-dual to each other. On the other hand, in Lorentzian signature, one can take dimensions 2 mod 4, and there one can have self-duality equations. And this is where the chiral fields appear in dimensions 2, 6, 10, and so on. Now, the self-dual fields are described by the equations that are the self-duality equation for a single form. And this is another problem, how to write the Lagrangian for these systems. And again, this is a problem studied by many people described here. And again, the Lorentz covariant first formulation is due to Pastisaro-Quintonin. Another formulation is by Sen, which is relatively recent. Now, if we go back to 4-dimensional electrodynamics and try to study the most general theory of nonlinear electrodynamics in 4 dimensions, we assume that we have no more than 2 derivatives in the equations. We also assume Lorentz covariance, Poincare invariance in general, and the most general Lagrangian we can write, and of course gauge invariance, since we are describing the theory in terms of the curvatures of the gauge potential, so F mu. So the most general Lagrangian one can write is a function of 2 variables. The 2 variables are the square of the F mu and F mu wage F mu in some sense. So these are 2 variables where star is the Hodge star. So this is the most general Lagrangian one can write, and any other invariant constructed from F can be described in terms of S and P. Now, the general equations of motion in this case can be understood in the following form. So since we know that our fundamental field is the gauge potential, so F is the exact form, which is the curvature of the potential, we know that the F is also closed. So that this equation means that part of the story. And there's the other equation, which is the Euler-Lagrange equation, which says that another 2-form G, which we get from variating the Lagrangian and taking the Hodge star. So this is also closed. And in general, one could think of these 2 equations are so similar that one can rotate them among themselves, as we can do in the free case. So in the free Maxwell case, this G would be just star F. So, and then we would have a rotation between F and star F, and we would have this symmetry. But now G is defined by F. It is a nonlinear function of F because Lagrangian is given by F. And so this rotation is not necessarily symmetry of this system of equations. And in order for it to be, we get an condition for extra symmetry. And this would be the condition that this Lagrangian is SO2 duality-symmetric. And this condition is derived by these people here. So, and it is basically saying that this is a very nonlinear relation for F. So we get that the F wedge F is equal to this G, which is a nonlinear function of F. And so actually this is we don't want to constrain F because it's our in our field theory it's arbitrary given by F is dA. So we want to constrain the Lagrangian from which we derive this G, and we get an equation for the Lagrangian, which is a differential equation, a complicated one. A general solution is not known, but by change of variables, one can write it in a simpler form. But eventually, what we know is that there are a few explicit solutions known, but the space of solutions of these equations is parameterized by a function of one variable, but we don't know the explicit solution. So the standard well-known solutions are Maxwell theory and Pornfeld theory. And a few more solutions I have found in literature by these people in '99, and a few more solutions we constructed with my student Montas last year in his master's thesis and in the paper we put out in May. But we will see later that we will suggest a different formulation where actually one would not need to solve the equation to write the most general nonlinear duality-symmetric electrodynamics. We will have it in most generality, and it will have a very simple form. Now,
can I ask just, is
sure.
it a necessary and sufficient condition? Because you say it's necessary, but if you solve this equation, then you have duality symmetry.
Yes, yeah. Any Lagrangian that satisfies this equation would describe a duality symmetric theory.
Okay, thank you.
But unfortunately, this equation is not easy to solve.
Yeah, this I understand.
So yeah, I will show actually in the other formulation that we use, we don't need to solve it. We will see it in a minute. So did I answer your question? Yeah.
Yeah, sure. I wasn't sure it was sufficient to solve this equation to have that. Okay.
Yes, it is.
Thank you.
So the different approaches for manifest duality symmetry I list here, and the approach by Pasti-Sarokin-Tonin has been the first one to have a manifestly Lorentz covariant description together with manifest duality symmetry. This is an example. So since so in the 4K plus 2 dimensions, 2, 6, 10, we don't need to introduce second potential. We just have one potential and we have self-duality, not twisted self-duality. That's why it's a simpler example I want to show here. This is a 6-dimensional one. So this is how the Lagrangian for Pasti-Sarokin-Tonin formulation looks like. So there is only a single auxiliary scalar field, and it appears also in the denominator with its derivative, which is not necessarily a problem by itself, but when trying to construct interactions, it becomes a bit of a technical complication. And we discussed this in the recent paper with Oleg Yevnin in a review where we compare different formulations. While generically, this is the most economic way to write a Lagrangian, which would give us the self-duality equations. There's a natural condition somehow appear in this formulation where that the derivative of this scalar, auxiliary scalar, should not be a null vector. Now, now I want to come to our formulation finally. So I want to just show the simplest form of the Lagrangian. So again, on the chiral fields, which is like 2D, 6D, 10D, and so on, is a Lorentzian signature space-time. So the Lagrangian has this form where we introduce not only the P form that we want to have, and we are in 2P plus 2 dimensions, so we can have self-duality. And we also introduce an auxiliary in other P form and an auxiliary scalar A. As you can see, this is less economic compared to PST, but we don't have this issue of dividing by the fields. And as I will show later, most importantly, this will allow us to construct most general abelian theories in a very easy manner. Nonlinear interactions would be much more simple to construct. So there are a lot of symmetries in this Lagrangian, and which is not surprising. We have many fields, but less degrees of freedom. So this Lagrangian, we claim that has degrees of freedom of just a chiral P form. It has two p-forms and a scalar, but it describes only half a p-form. So the way it works is that when we derive the equations of the three fields involved, we can notice that some linear combination of the two p-form equations gives us an expression which has to be zero due to on-shell condition, which is the A wedge and anti-self-dual form. So, and there is this interesting property that we use. This is also used very much in the PST formulation, that wherever your vector is not null, then if it's wedge with the self-dual or anti-self-dual expression is zero, that implies that that expression itself is zero. This can be very simply explained in a sense because it is basically any self-dual or anti-self-dual expression can be described by directions, and since it's so it can be divided into part that has some leg in one direction and the part that it doesn't. If you say that one of them is zero, by self-duality condition, the other will be also zero somehow. This is some very on fingers to explain why this happens. Otherwise, one can just use some simple Schotten identities, or like there are many ways to show this. So this is the main technical trick. So our equations are generically second order, and suddenly they become first order because we do this trick. We have the equation which implies some first order equation. And now when we have this first order equation, we can plug it back into the other expressions. First of all, we see that the equations of motion for the A field, this small A field, will be automatically satisfied when the other two are satisfied. This indicates that there is a shift symmetry for this A field. So we have a field in the theory which has a shift symmetry. We can shift it by arbitrary function, and it can be compensated by the other transformations by other fields, which is actually written here. So delta A is equal to phi, and then we have certain transformations by these fields that compensate it. Now, this equation plugged back into these other on-shell conditions actually implies that we have also this condition, the A wedge dr equal to 0. Given the symmetries that we have, I will not go into technical details, but it's straightforward to show that this implies that also the R field is pure gauge. So there is at least a gauge where we can put R equal to 0, and we get just the only field that is surviving is the A field, the 1p form, for which the equations become just self-duality condition. So this proves that the Lagrangian we wrote describes the self-dual p-form theory. Now, if we want to extend this to arbitrary dimensions and arbitrary p-forms, there is also a very logical extension with the, again, doubled set of fields. So now we need to have not the self-duality equation, but the duality equation, or twisted self-duality equation, where we have this two different forms, p form and t minus 2 minus p form, and they should be dual to each other. And this duality equation would already imply that both satisfy corresponding Maxwell-like equations. So this Lagrangian written here contains not only these two potentials that we want to introduce for this twisted self-duality, but a second copy for each of them. But this will eventually, with the same mechanism as described above, this will eventually turn out to be pure gauge on shell. And then we can gauge fix and then go to the gauge where all the auxiliary fields decouple, and the only equation is this equation written here, which is the twisted self-duality equation. Now we don't have any restriction on either dimension or the p form. It's just that the only description restriction is that the sum of the ranks of A and P is t minus 2. which makes sense for this equation, otherwise it wouldn't. So now this mechanism we can apply to 4-dimensional electrodynamics. Then if we take one form, its dual is again one form, and then we can write just two one forms and their second copies, because the formulation requires second copies that will eventually be pure gauge fields. And then we have 4 vector fields and 1 scalar. And this is the Lagrangian that we write. This is the describing Maxwell theory, free Maxwell theory, using basically 17 different fields. So 4 vectors each have 4 components, 16 plus a scalar. So originally we have just 2 degrees of freedom, and in order to have Lorentz symmetry, we were using 4 degrees of freedom, the vector potential as a fundamental field, introducing redundancy and gauge symmetry, but having Lorentz symmetry manifest. Now we also have the duality symmetry manifest, and that requires extending in the number of fields we are using. But eventually, yeah, we have this Lagrangian with 17 components altogether, but they describe only the 2 degrees of freedom of the free Maxwell theory. And in on-shell, we can again see that this extra fields will be pure gauge, so we can gauge them to 0, and then the equation is left is just Maxwell twisted self-duality equation, which is equivalent to Maxwell equation. Now, the extension of this to arbitrary nonlinear electrodynamics can be constructed noticing the following. The second term here has, so there's a set of symmetries. I showed them for the chiral fields. Don't want to bore you with a lot of formulas. So the second term here is invariant with respect to almost all the symmetries, except for the shift symmetry of the scalar field involved. So at the same time, the first first part also separately is invariant with respect to all of the symmetries except for the shift symmetry of the scalar, and only this combination is invariant with respect to also the last symmetry. Now what we are saying is that, okay, so this expression by itself, this H, is invariant with respect to all the symmetries except for the scalar shift. So let's take, instead of its square, let's take arbitrary function of it, and just that, adding to this second term, but then impose a condition that we also have the scalar symmetry and see what is the most general theory we will get. And indeed, this will allow us to build the most general nonlinear electrodynamics. So this is the first, well, here it was the second term. This term I wrote now without indices. And then this is the most general nonlinear Lorentz covariant terms we can write, basically Lorentz scalar built from this H. And now you can see that yeah, there are basically 6 different scalars we can build, because this A and B run 1 and 2, and they're symmetric, but in this U and V. So each of them contain 3 different components. And now we have 6 components here. So we have a function of 6 variables in the Lagrangian. But we want to impose extra symmetries and see where we get. So the equations of motion for this general Lagrangian for equations of A fields and R fields are given here. And the last equation of this A field is given here, where this K is this expression. So this F U is just derivative with respect to U, and that V is derivative with respect to V. And we also impose this condition because there is a redundancy. U12 is the same as U21, so we just discard the U21. This is just some technical details. So that then what we see is that this, again, the combination that we used to take in the other example I showed, again shows this structure where this K is now given here. So now we want to jump from 2 derivative equations to first order equations with 1 derivative. So, but that is only possible when this K itself is self-dual or anti-self-dual. So we impose this condition so that we can jump from this equation to the equation that K is 0, which is already first order equation, using the same trick as before. And this will be possible if our K, which is given by the theory, is self-dual. And this condition by itself would also imply that this equation of the last scalar field is redundant, so we have shift symmetry for that field. Because in the equation of the last field, there is K. So if K is 0, then K is equal to 0 is implied by other equations. So this equation is redundant now, which means that there is shift symmetry. Now that we only have the condition that this self-duality of K should be satisfied, and that would give us like list of possible theories described in this language, which are nonlinear electrodynamics. And this condition can be translated into this function f of 6 variables in this language. And we see that it's basically 4 equations on this function of 6 variables. They are like equations that are first order differential equations. We can simply solve them. And we get the final result is a Lagrangian that depends on a function of 2 variables. The Lagrangian is the Maxwell one plus this, the Maxwell as the one I wrote before in our language that contains all of these fields. And another function of 2 variables where these 2 variables are written in this form. So there is a this 2 form that is star h1 minus h2, where h was this f plus aq that I defined before. And it is basically this g is an arbitrary function of this, and the small g is arbitrary function of the big G. And then you can construct 2 different scalars from big G, and these are lambda 1 and lambda 2. And so this G is basically a function of these 2 scalars, since it's a scalar by itself. And this will give us the most general nonlinear electrodynamics. We did not impose any duality symmetry at the moment. We are just imposing that it has the same number of gauge symmetries, nothing about the global ones yet. Same number of gauge symmetries as the original Maxwell one. Therefore, it would have the same number of degrees of freedom eventually. And indeed, if we compare the result with the original nonlinear electrodynamics written in terms of 1 variable, one gauge potential, where it is given by a function of 2 variables. So again, we have a match, but we will make it this very exact in the sense that we can show how to relate these 2 formulations. Now the duality symmetry can be imposed in a different way. So if we want to just impose the discrete duality, then these 2 variables that we constructed, they transform just changing the sign. Therefore, what we can say is that we can choose a function that is even in changing sign of both variables. So it only has even overall powers of the 2 variables. And that's it. Any such function of 2 variables would satisfy discrete self-duality. But when we want to impose continuous duality symmetry, as defined before, then we get that actually it rotates lambda 1 and lambda 2. And we will have basically a component, which is the radial component in the lambda 1, lambda 2 plane, this W, which will be invariant under this rotation. So we can take an arbitrary function of 1 variable given here, and this will define as a Lagrangian with an explicit one, any function of 1 variable. This defines a Lagrangian of most general duality symmetric electrodynamics, arbitrary nonlinear in 4 dimensions. In fact, we can take it to be even polynomial in this W. For example, the standard formulation, when we try to solve this equation, which is also sometimes people call it Courant-Hilbert equation because it appears already in the book of Courant and Hilbert, unrelated to the electrodynamics context. and the implicit solution is known. So here we don't need to solve that Courant-Hilbert equation, and we also know that there are no polynomial solutions to Courant-Hilbert except for Maxwell. So here we have also polynomial expressions we can write in the variables that we described, and we have many possible, infinitely many possible duality-symmetric theories, given by this function of one variable. And this can be also defined as if we introduce this curly A, J, B, which is basically the contraction of two of this anti-self-dual expressions made from the other age, then this can be understood as a square root of the negative determinant of this age. The interesting thing here for me is that I don't know why this AJB, which is kind of like a two-dimensional metric, it necessarily has a negative determinant, so which means that it has a Lorentzian signature. I have no clear understanding why this happens, but on the other hand, I have a clear proof, because when I compute this W in terms of lambda 1 and lambda 2, I know that we get a positive number. We get a real number. So here determinant H cannot be positive. So just a side comment. We can also require conformal symmetry from general nonlinear electrodynamics, and in this language, this basically implies this equation on the general function of two variables. And what we compute is just we compute the energy momentum tensor and put the trace to 0. So that would imply conformal symmetry. And this gives us this equation. And this has a general solution, which is again parameterized by a function of one variable. But when we want to impose both duality symmetry and conformal invariance, then we get to the only solution, which is given by a linear function. So we have a function of one variable, but on it there is also a conformal condition, which is this one now. Then the only one that satisfies it is a linear function, delta times W. And this is the most general conformal and duality symmetric electrodynamics. Just 1 year before us, people found this mod-max theory, which is the modification of Maxwell theory with conformal and duality symmetry, but in the standard single potential language. We will relate this to the other one. And so again, the story goes very similar to the free case. So it turns out that even though we have this crazy nonlinear arbitrary functions in our Lagrangian, still the equations imply that the auxiliary field is pure gauge. And then the most general electrodynamics equation in the first order form is given here, like star F1 plus F2 is basically a function of star F1 minus F2. And this is, has given us a hint how to very simply solve also the most general case for arbitrary p-forms, but I will come to that. So where now G1 and G2 are actually different derivatives of this function G. But now we can use this equation. Now we have an equation that only contains F1 and F2. We don't have auxiliary fields. Now we can use this equation to solve F1 in terms of F2. Then the equation Tf1 is 0, right? Because it's a curl of potential, will imply for us an equation only for F2. This we can think of as the Euler-Lagrange equation from a single potential theory, and then we find the connection with the single potential story. So if you have a single potential Lagrangian, which is given by a function of two variables, which are in this context, we take this variable to be the F2 of our theory, then we call alpha and beta different derivatives of this Lagrangian, and then the equations of motion can be connected to this equation of motion. And this gives us algebraic relations between the two, not the Lagrangians, but their derivatives. And this can be in principle solved, but also the variables, lambda1, lambda2 that we had become some algebraic expressions in terms of the alpha, beta, and S and P invariants of the single potential theory. While whenever we have also duality symmetry, this simplifies a bit because we only need one variable, which was this W, and it is given in this form. Now, when we have only this duality symmetric case, we can actually show that we get the equations that connect these two formulations. And these two equations, naively, they should be used to find, if we know the standard formulation, find the manifest duality symmetric our formulation. But since we have more equations now, we can actually exclude the H and W that enter only in the duality symmetric theory and get some condition on alpha and beta, which is just for the single potential theory. This condition is exactly the Courant-Hilbert equation that is needed for the duality symmetry there. Since we now assumed that the other theory is duality symmetric, this relation implies that also this theory, single potential theory that we have is duality symmetric. But in order to have the manifest duality symmetric theory, we don't need to solve this. We need to solve this when we want to go back to the single potential formulation. So this is intrinsically a problem of the formulation, we don't really need to solve this equation for having some theory of duality symmetric description. So this one can argue that implies that our formulation is more fundamental in some sense. And then the two equations written above can be derived into two equations below. So one is the Courant-Hilbert equation for the first theory, but the other can be used for the translation from one theory to another. This we can actually do for examples that I mentioned. For example, if you have conformal and duality symmetric electrodynamics, then our expression is given here in the manifest duality symmetric language. But if you want to write in the single potential formulation, this is known also, but we can also show exact translation from one to another in the way written in the previous slide, like how to map each function. And indeed, we see that when we take this delta to be cotangent hyperbolic of gamma half, we get the corresponding single potential Lagrangian to be this, which is known as the modmax Lagrangian in the single potential formulation. What is interesting here extra is that, I have only 10 minutes left. And what is interesting that here we have an extra point, delta equal 1. There's absolutely no problem in our Lagrangian with delta equal 1. The problem is that we cannot translate it into a single potential formulation. So what we actually did notice is that there is a separated known example of a theory that has both duality symmetry and conformal symmetry. In fact, the duality symmetry there is extended to SL2 instead of SO2. And this is called Bialinski-Pirula theory. And indeed, this case when delta is 1 reproduces that is equivalent to that theory. It's just that theory does not have a simple Lagrangian description with a single potential. You need to introduce some Lagrange multipliers, and which imply that both S and P are actually 0 in that theory. And it is also called by the author as a theory that describes photon dust. It's a theory which is does not have a linearized version. I mean, you cannot linearize it to Maxwell plus some corrections. It is an intrinsically nonlinear theory, which is the kind of tensionless limit of Bornfeld theory. Anyway, so our formulation simply describes also that without any complication, while in the single potential formulation, there's no simple formulation for it. Next, we also know that there's this generalized Bornfeld, which is a Bornfeld theory with an extra parameter. And when we take the tension in this theory to infinity, then we recover the mod max. When we take the tension to 0, then we recover the Bialynsky-Pirula theory. And but for general T, the generalized Borningfeld Lagrangian looks in this form. I try to make it as compact as possible, but anyway, introducing these variables U and V. And what puzzle does was that it's not a so simple expression. When you do this nonlinear electrodynamics, you always expect that Borningfeld is the theory that is the most canonical and simple and interesting example of nonlinear electrodynamics that satisfies very weird tests. It's like the only example of nonlinear electrodynamics that does not experience P-ref regions. And so there are many properties that is very unique for this theory. So in our language, we would expect to get a function, HW, which would describe Borningfeld theory. And we were very curious to see what this function would be. What happened is that we were not able to find a simple function, and we were very puzzled about it, but eventually we found the implicit formulation, implicit function, which is given here below. So H is given through lambda, while W is also given through lambda, and it looks very simple and symmetric in some sense, but H written in terms of W becomes like messy. So I guess there might be some smart way to maybe another auxiliary field would help or something to make it really nice. But at the moment, this is the nicest possible way we can write the generalized Borningfeld. And then when you put gamma equal to 0, this would be just Borningfeld. So, okay, next, so we can generalize this whole story for the electrodynamics to chiral p-forms. Chiral p-forms are a good example because one can do any p-forms in any dimensions and so on, but chiral p-forms are a tricky example, and that's why I want to show just that and how simple the solution is. So as I showed in the beginning, the free Lagrangian for the chiral p-forms is given in this form in our language. And the general nonlinear Lagrangian is given here. So we add an arbitrary function of an anti-self-dual combination of this F plus AQ. And that's it. This satisfies all the symmetries, everything, and this is most general interacting theory we can write in this language. What was very surprising to us, this we understood after understanding the 4D electrodynamics and noticing some interesting properties. So what puzzled us is that we see a very simple expression for the covariant equations that comes out from here, which we haven't seen anywhere. This was not available in literature as far as I know. So the expression is that F plus star F is an arbitrary function of F minus star F. This is very natural. Well, it's not arbitrary function because you want to have as many equations as you do in the free theory where this right-hand side is 0. So, so for that reason, you want to have this right-hand side also to be self-dual as the left-hand side. And it is a function of anti-self-dual variable. And indeed, we can actually see that in our formulation, this equation that comes out, this F is actually a derivative of a scalar by an anti-self-dual parameter, which automatically is self-dual. So it satisfies all the properties of the natural equation. The only question is this the most general equation? In principle, one can have a self-dual function of anti-self-dual variable, which is not a derivative of a scalar. And indeed, this is generically true, but not in 6 dimensions, because in 6 dimensions, the most general self-dual function of anti-self-dual variable is a derivative of scalar. So this is the most interesting example for many reasons, and also most studied. And for just curiosity, I added this quote from Perry Schwarz 96, where they did an incredible job of finding these theories in a non-covariant way, in a five-dimensional Lorentz covariant way, where it becomes much more complicated and messy. While compared to what we write here now is like, we don't need to do that anymore. It's just back in the time, people didn't know and it went in the other way. So it's surprising how like the prevailed point of view was that you cannot even have equations of motion that are Lorentz covariant, while we can see how simple they are eventually, these equations of motion. And and then the statement that I want to make is that up to t equals 6, this covers everything, but it's a bit inaccurate because there is some subtlety in 4 dimensions. But in 4 dimensions, you can have more than that for the electromagnetism that I described, except that whatever you can have more than that is not Lagrangian in any of the formulations. So this is something that puzzles me. I want at some point try to look at it, but it's generically interesting that the first place where this somehow manifests itself. While in higher dimensions, generically, it is not true that the most general equation you can write, which, I mean, maybe there are more physical conditions that would restrict us to choose only those that are derivative of a scalar. But at the moment, I don't have this in mind. What I can say is that if I can solve algebraically f plus star f in terms of f minus star f, and I write this kind of equations, it satisfies all the physical properties I can imagine, then this is a consistent equation. While our formulation gives only those equations for which we have a scalar Lagrangian, and therefore the right-hand side comes as a derivative of a scalar function. So for dimensions higher than 6, generically, this does not give most general equations I can imagine, although I don't know if those equations might have other problems. These ones are consistent, they come from Lagrangian and so on. So still, this is a much larger class that, than ever described in the literature. And I want to also comment on relations with other formulations, which is the subject of our review with Oleg Evnin. So one of the advantages that our formulation has is that in general, interactions are given by arbitrary functions of certain variables. And this is very easy to construct. Instead, for example, in PST, that's not true. In PST, you have somewhat similar situation like in the formulation of electrodynamics in terms of a single potential. You still have to solve this equation by Courant-Hilbert, which generically doesn't have a simple solution. While in a somewhat similar situation happens in the PST formulation of general chiral P-forms. Though the equations are known, some solutions can be found. So again, there is some progress there, but in general, you cannot immediately write all possible interactions. And in fact, there is the sense formulation where you can also write arbitrary function of some variable and gives you all the interactions. But it has other disadvantages, which are not the disadvantages of neither our nor PST formulation. So the auxiliary fields that appear in sense formulation, they are not gauged away. They stay dynamical and they are caused. It's just they decouple from the main system. And we can think of this as like not posing any problem, but also, I mean, you have extra degrees of freedom that in principle might cause trouble in some other setup. But also one of the advantages that I think is there for PST and for our formulation as compared to sense is that we use gauge potentials as fundamental variables. In sense formulation, the physical degrees of freedom are encoded in a field which is not the gauge potential, but is a curvature, and it's a fundamental field. So in that sense, I think that it is hopeless to try to generalize sense approach to non-abelian case. While in our case, there is still a chance that we can construct non-abelian extensions of this story. So to summarize, I think that the choice of the variables, fundamental variables, is very important. And the free Lagrangian is basically all about that. What are your variables that you're describing your system? If you write a free Lagrangian with these variables and then you extend it to interactions with many standard ways one can do that. And another message I want to convey is that the Lagrangian can actually manifest both duality-symmetric and Poincare symmetry, or in general, not necessarily duality symmetry, but democracy between electric and magnetic degrees of freedom and Poincare symmetry. And this does not have to compromise other properties like polynomiality of the Lagrangian and so on. And okay, so Ami is now here from the train, I guess. So abelian self-interaction in our formulation are simple and tractable. This is the main advantage, the main result at the moment. And we had used this also to write simple Lagrangians for type 2 supergravities in 10 dimensions with Friedrich Wallach. But one most important advantage of that, using this formulation for the supergravity there, would be in the constructing next orders that come from alpha prime corrections, because in this formulation, these abelian interactions are very simple to construct. And this might open technically new road to getting the alpha prime corrections. Also, this formulation has much more symmetries, and they are also restricting in some sense possible higher order terms. So this might be very useful. A list of related ambitious problems that I want to attack eventually is the democratic formulation of non-abelian cage theory, which is a bit I mean, it's known to be a very hard problem, or there are many reasons to believe that there is no solution to it. There's a similar situation exists for the interacting theory of non-abelian chiral p-forms or extensions of duality symmetry to gravity and higher spins. But yeah, we should try, and I will be happy to discuss with anyone who is interested in these problems. Thank you.
All right, let's thank Karapet. Do we have questions? Maybe I can start with a quick one. I don't know if you mentioned this already, but this Hilbert-Courant equation, for what did they use it? I mean, this is really orthogonal to your talk, so I apologize.
Yeah, just.
But you said that it has nothing to do with electrodynamics.
They have a huge book on on just the differential equations, and there is an example there.
Oh, I see. Study it purely as an equation. It's not something.
Yeah. It's
okay. I thought maybe there was a geometrical problem.
No.
Okay.
Yeah. This is the equation in this language, but it can be simplified if you pass to this UV variables. Then it's just LU LV equals to -1. And that equation does not have a simple general solution.
Okay.
I mean, not an explicit solution. There is an implicit one by Courant and Hilbert.
And so I have a more general question about this way of thinking. I mean, this shows how little I know about the field. But so having these formulations, which are, you know, like Lagrangian, and you see all of the symmetries in this, apart from, of course, this being very nice if we can get it, but other things that we can then like learn that we couldn't learn otherwise? Or is there something that like make studying the setup much more simple? Like, for example, let's say the two form in 6D or things like this.
Yeah. To me,
The alpha prime corrections, but
yeah, to me, the motivation comes from the ideas related to non-abelian cases where I don't yet have any result to show. So, one can be very skeptical that this will lead to somewhere. On the other hand, for abelian case, we have managed to get very simple expressions for general interacting theories that has been a problem until now. The Perry-Schwarz formulation, it's very complicated, and again has exactly the same situation as with this Courant-Hilbert problem. You have a function of two variables, you have a general equation on them, and it's exactly the same equation as Courant-Hilbert. It's just about 5-dimensional story, but the 5-dimensional description of actually a 6-dimensional story. Instead, what we have is that everything is 6-dimensional, Lorentz covariant, and very simple. Just you write a function of one variable, arbitrary function, and you have all possible interacting theories. So this is one example where this has been useful.
Okay, very nice. Do we have more questions?
Yeah. So, well, I guess one of my questions was about the non-abelian, but you.
What can you say about quantization? What can you say?
Okay, so the question was, what can you say about quantization from Ami? I don't know if I got it.
Yeah, at the moment, almost nothing. So for quantization, even for the free theory, what would one usually do also in the PST formulation, and here I didn't think of anything better, is to gauge fix first, which means losing Lorentz symmetry and then quantizing. But I am hopeful that one would be able to find a more a formulation of quantization without compromising. With manifest Lorentz covariance. So yeah, but at the moment I cannot say much about that.
So I had one question about the coupling to other fields, like to matter fields, because so you can phrase, for instance, Maxwell with all these additional fields, and now if you want to couple to some electrons or something,
coupling to electron is not a problem. So this is an ongoing work. Sorry. Okay.
Okay, continue.
Coupling to a single type of matter is not a problem, even if it's a monopole or a electron that has only electric charge or a dion. But if there is only one type of charge, or in a sense, the ratio of electric and magnetic charges is just given by one number, then we can couple anything you want in the same way as standard electrodynamics couples to electrons. What happens as a problem is when you try to couple two different types of dions, like electron and the magnetic pole. And when it's well known since Dirac, then when it's just the single particles, you can study and see that actually it's possible with some quantization condition. But when it's a classical field, you have arbitrary currents and so on, which have arbitrary structure, then there is a conflict. And we are trying now to understand that, but as long as all other formulations, whatever they can do, we also can do. But beyond that, at the moment, it seems like there's a little result, so I cannot report much. But if you just want to couple standard QED, we can couple standard electrons. It's not a problem at all.
And so, for instance, because if we wanted to understand, for instance, in 6D, the 2,0, the supersymmetric theory, then you would need to add all the other fields. So there are several fields, but this is in principle doable then, because it's only.
I think so, yeah. So the duality-symmetry equations, I think these are known for also like free 2,0 theory. So as long as we know what is in the right right-hand side. So we have star h minus h equal to 0 in the free case. If you give me what is the right-hand side, which also should be anti-self-dual, then I can write you a Lagrangian that gives that equation.
Okay, so
But,
the rule is that
yeah.
you couple it to this h, which is kind of the difference between the two copies of the gauge field, something like that. This is how you couple matter fields.
H. Sorry, can you?
No, I don't know. I don't remember what is
So,
h in your h was the difference between f and g. Yes, it's
F and Q. So okay.
F and Q. Sorry. Yeah.
So yeah, when I say H, I meant this F plus AQ expression. Okay, here. So on shell, this R is 0. The R is the Q. So yeah. So on shell, this will drop, and we have only F. But yeah, what I was saying is that if you give me what is the right hand side of this equation, if we forget about the Q at the moment, F minus star F equals to, if you give me what is the right hand side in any matter that you introduce, then it's straightforward to write a Lagrangian that would give you that equation. So this much we know. I didn't go into detail.
Really the non-abelian. The
non-abelian, and when you have both types of but electrically and magnetically charged and different current somehow sources that have different ratio of electric and magnetic charges. This is a problem, and non-abelian, yes, it's a problem at the moment.
So how about multiple numbers of fields? Here you dealt with one.
Yeah,
you understand the question?
So if we have abelian interactions for multiple fields, that's one story. There we also can quickly get a lot of results because it's straightforward to extend. But whenever we want to have non-abelian interactions, there it's I mean, we don't yet have much results in that direction. Yeah. That is a bit more complicated in general. But if we want to have several fields that interact in just contract their curvatures in the same way as in the single potential formulation, for example, of electrodynamics, this we can do straightforwardly. Yeah, but non-abelian case is yet to be understood.
Yeah, there is this dynamical mechanism where the number of fields goes from n to n cube, right? So that's a feature known to this type of fit to the string theorists. But the question is, how can this arise from some Lagrangian, if at all?
How this can arise? I didn't hear the rest.
How much can you hear me? So I'm saying the simplest dynamical mechanism is where you start with the linear number of fields n, and then at critical points, the number of degrees of freedom goes from n to n cube. And the question is how such a dynamical mechanism can be seen from this formulation. So that's related to Antoine's question about the zero-K fields. Did you hear what I said?
I'm not sure I heard well. So there is a problem related to it. You take multiple fields and then you have some kind of symmetry breaking. Did I understand correctly?
There is an increase. There is an increase in the number of degrees of freedom from n, so linear in n, to n cube.
N cube.
And so the question, how does this arise? It's very similar to gauge theories, where the number of degrees of freedom grows from n to n squared. So
N squared.
And over there you have the Higgs mechanism.
No, I haven't thought about that. So Yeah, I think generically that this is a question about the non-abelian case. I think so. I'm not sure, but yeah, I haven't thought about this.
Another question which arises is how do you deal with anomalies? So that's the reason I asked for quantization. So, did you
How
hear
do
me?
I deal with what?
Anomalies.
Oh, yeah, no, didn't think of that either.
So first you need to quantize, and then you find that there are anomalies.
Right. Yeah.
So,
Yeah, and it's not so clear here at the moment. But, yeah. One of the weird features is that already the free theory, so already the free theory is not actually quadratic. So we are familiar with the standard formulations where the free Lagrangian is quadratic. We can kind of quantize in the standard way. But here somehow, since this A field, for example, has an arbitrary shift symmetry, we can gauge fix it. Then we will have a quadratic expression, and then we can quantize. And this is what they do also in the PST. But the gauge fixing of this A cannot be, I mean, it will break Lorentz. So this is a general problem that we face, which is shared with PST formulation. Yeah. At the moment, I don't know the solution. So, yeah.
okay,
Can I ask about odd dimensions?
In odd dimensions, one can have duality, but there's never self-duality. So basically, the forms that are dual to each other are always different rank. So yeah, there's no chiral fields. There's no like twisted self-duality like in the electrodynamics case, but the same approach works. Here, one can write this Lagrangian where T can be odd. So we can have a P form and T minus P minus 2 form, and you will get eventually this equation from this Lagrangian. So so in 3 dimensions, for example, one can have a vector and a scalar, and in 5 dimensions, scalar and the 3 form or vector and the 2 form, and they can be dual to each other. Yes. And again, arbitrary nonlinear extensions that are abelian are straightforward.
So do you like the analog of this nonlinear? For example, Chern-Simons is kind of like a. Do you find something which is nonlinear but less exotic, like maybe some duality for Chern-Simons type interactions?
Less exotic in which sense? So
in the sense that it's more like Chern-Simons theory is something that is more familiar. Yeah, I mean, exotic is depends who you ask. Right?
So I mean, I would define it's less exotic what we have done so far, which is the abelian interactions, but more interesting would be the non-abelian interacting story. I don't know any kind of. So yeah, there is a issue with the Chern-Simons couplings, which is also not yet solved. So in 5 dimensions, for example, there is a Chern-Simons cubic vertex for the spin 1. And this is, on the one hand, it is abelian. On the other hand, it is not manifestly cage invariant. It's a cage invariant up to boundary terms. So this case is different from the most general abelian interactions I described. So this may be one special case that is in between abelian and non-abelian, because one can try to do something that's a bit more complicated than the abelian, but still probably simpler than the non-abelian case. I don't know if this answered your question, but this I have thought about, but didn't seriously work on.
let me press more on quantization. If there was an attempt to quantize, would there be a preference between canonical quantization and path integral formulation?
I believe that naively path integral quantization might apply here. So then we don't really need to kind of break Lorentz symmetry. The only problem is that in the path integral, you would take integral with all possible configurations, and there is a zero measure part of this theory where your field A has a gradient which is null. And there the number of degrees of freedom is different in the theory. So I don't know how this like kind of is dealt with in the path integral quantization, but if we somehow try to neglect this subtlety, in general, probably this would, yeah.
See.
Okay, do we have more questions for Karapet? Maybe anyone in the train? Can you ask them?
Neil should be on another train. This is still here.
I see Neil.
Yeah.
Oh, wonderful.
Same arrangement, same setup. It's just an hour ahead.
I see. Okay, so you're not in the same train. This would be even better. Wow, we didn't hear you, Neil.
I didn't. Yeah.
Okay, it seems his connection is a little worse.
Well, we just started moving, so
Okay.
I might just.
Well, but if we have no questions for Karapet at the moment, then let's thank him again for this nice talk. And I will stop the recording.